Let's do problem number 17 on page 102. And here it is in the book. All right. It says, a ball is tossed from an upper story window of a building. The ball is given an initial velocity of 8 meters per second at an angle of 20 degrees below the horizontal. It strikes the ground 3 seconds later. A, how far horizontally from the base of the building does the ball strike the ground? B, find the height from which the ball was thrown. And C, how long does it take the ball to reach a point 10 meters below the level of launching? Okay. So let's, I've kind of set it up here already, given find and solve. Let me zoom out. So I got a little more room here. Okay. Okay, so let's do part A. Now this is just a projectile motion, and if there's only one equation for delta x, and that is v naught x times t. Well, what is v naught x? V naught x is v naught cosine theta, and then times time. And now I'm ready to plug in values. Delta x equals, well, v naught was given to be 8.00 meters per second. We only want that horizontal component, right? So we're going to multiply that by the cosine of negative 20 degrees. That's the launch angle. And then we'll multiply it by time, which is 3 seconds. Of course, that'll cancel that. And so delta x turns out to be equal to, what was it, 22.6 meters? Is that right? Okay. And you plug it into your calculator. Box answer. Now, I think one mistake that some people made that I saw in this one is, you know, this cosine is really important, right? So you gotta find the horizontal component of the thing. So you could, when you write, you know, what mistake did you make? You would say, the mistake I made was not using the horizontal component of the initial velocity. You fix it, and then you say, okay, what did you learn from it? In projectile motion, you have to make sure that you're using the x and y components of the initial velocity, right? You have to break up the initial velocity into x and y components and use them appropriately. So let's do part B. And we want the height here. So really the height here, well, from here to here, we'll call that delta y. And what do I know? Well, I can figure out the initial velocity in the y direction, and I'm given time, and I know the acceleration. So I can use the third kinematic equation. And now I can plug in values. The initial velocity in the y direction is v naught times the sine of the launch angle, which is 8 meters per second times the sine of negative 20 degrees. You got to keep that negative angle there. It doesn't affect the x component of the initial velocity, but it does affect the y. And let's see, did you do that? It was negative 2.74. I believe was the initial velocity in the y direction. So now I can plug all that in. Delta y equals negative 2.74 meters per second times time, which was 3 seconds, plus 1/2 the acceleration, which was negative 9.8 meters per second squared, times time squared, 3 seconds squared. And so delta y, when you do all that, equals negative 52.3 meters when you type all that in. But this is how far it dropped. So I just say, therefore, H equals 52.3 meters. Because I put it in terms of H in my drawing over here. If you, some of you said, called it y sub 0, and solve for y sub 0, say y final is 0, so what is y naught, and you solve for it, and you get the same answer. That's perfectly fine if you did it that way. Now for part C, oh, I forgot to put it in given. We want to know, it says, how long does it take the ball to reach a point 10 meters below the level of launching? So we want to know t when, and what we're going to do is we're going to go down 10 meters, right? So this is negative 10 meters. When delta y equals negative 10 meters. It dropped 10 meters. And it's really important, right, when you do this. This is why I like drawing a picture and laying out the problem very, very nicely and just really methodically go through and think about it. Of course, I'm skilled at this, but as you go through it, draw a picture and write what's given around that picture. So we want to know what t is when delta y equals negative 10. So we have, we'll just use the third kinematic equation and solve for time. So we have delta y equals v naught y times t plus 1/2 a t squared. So now let's rearrange this. I'm going to call this 1/2 a t squared. And I'm just putting it in the form that where we can use the quadratic formula. And then plus v naught y times t, and then minus delta y equals 0. So now I'm in the right form. Now what is 1/2 of the acceleration? It's 1/2 of 9.8 is 4.9. So this is going to be negative 4.9 meters per second squared times t squared. And then what is v naught in the y direction? Well, that's negative 2.74. So minus 2.74 meters per second times time. And then minus negative 10, so that's going to be plus 10 meters equals 0. Now here's your A, your B, and your C for using the quadratic formula. I'm not going to go through that. I'm going to assume that you can do that yourself, or you can use your calculator. There's a solve button, or there's a quadratic formula, but somewhere on your calculator. All of you have scientific calculators. They all do the quadratic formula for you somehow. If not, you can just crank through it. When you do, you get t equals negative 1.74, and then or seconds, or 1.18 seconds. Now, which one are we concerned with? Well, we want to go back in time. If I were to we want to go forward in time. If I were to go back in time, this actually makes sense in that if this was a full, here but if you were to go up, like it would, I have to draw on my table here, but if I finished this, if I were, if instead of throwing it from here, it was launched like from the ground or something, it would come like this. And so it would be at 10 meters back here and over here. So there's 2 times, but only one of them makes sense in the context of this problem. Does that make sense to everybody? All right, so we're going to say t equals 1.18 seconds. So I'll put use quadratic formula. or your calculator. So there's the whole thing. Pretty, okay. Any questions? Okay. That is all